In this video, we continue our studies of algebraic geometry with a discussion of the relationship between polynomials and affine space. The material in this video is from a book that I am outlining for myself and for you while I'm at it. It's Ideals, Varieties, and Algorithms by Cox, Little, and O'Shea. And it doesn't have an edition, so I bet that means the first edition. Okay, so last time we talked about the properties of a field K. Basically, a field is just a set where the expected properties that we're accustomed to, like addition, subtraction, multiplication, and division, they all hold. So a few examples of a field include the set of real numbers. That's a field, because you can add, subtract, multiply, and divide real numbers, and you always get a real number back. And that also works for the complex numbers. That also works for the rational numbers. So these are all fields, and we discussed that at the beginning of the last video. And then we talked about the definition of a polynomial. Now you're probably already familiar with polynomials, but now we're making it a little bit more abstract. Rather than thinking of a polynomial in terms of one variable, x, we're going to talk about polynomials in terms of two variables, x and y, or three variables, x, y, and z, or in general, n variables, x sub 1 through x sub n. And we're going to say that these polynomials have coefficients in a field K. Again, that's just a set where all of the typical properties of addition, multiplication, subtraction, and division, they all hold. And the notation that we use for that is this. Now, in order for this to be a polynomial, this has to be a finite sum. It can't be infinitely many terms. We are adding up these terms over a finite number of n tuples alpha. So alpha is actually, you can think of it as a vector or an n tuple. It's got entries alpha sub 1, alpha sub 2, alpha sub 3, all the way through alpha sub n. And these numbers alpha sub 1 through alpha sub n are non-negative integers. So basically they're natural numbers, counting numbers, 1, 2, 3, 4, and so on, or they're 0. And this x to the alpha is shorthand for a product that looks like this. If we have n variables, x sub 1 through x sub n, this is just going to be a sub alpha is just some number in the field. So that could just be like a real number, like a 3 or something like that. And x to the alpha is shorthand for x sub 1 to the alpha 1 times x sub 2 to the alpha 2 times x sub 3 to the alpha 3, all the way through x sub n to the alpha n. So just to give you a concrete example, here's a function. So this is a function of three variables, at least three variables, x, y, and z. The coefficients alpha or a sub alpha are 2 and -1. And this x squared y cubed would be represented by a single x sub alpha, where alpha is actually the vector with components 2 and 3, and x sub 1 and x sub 2 are written as x and y. And then this one over here could also be written in this way, but since it doesn't have any x's and it doesn't have any y's, we might think of it this way. We might think of this as -1 times x to the 0 times y to the 0 times z cubed. And so alpha sub 1 would be 0, alpha sub 2 would be 0, and alpha sub 3 would be 3. And that vector 0, 0, 3, that would make up our alpha. So this represents x to the alpha in this case. Or in general, it's just the part with the variables in it. And the coefficients are the numbers that are out front. And those numbers belong to some field. 2 and -1 belong to this field and this field and this field. So this would be a polynomial with coefficients in any one of these fields. We could think of it that way. And we have at least three variables, which we typically denote by x when we're only dealing with one variable, x and y when we're dealing with two variables, and x, y, and z when we're dealing with three variables. But once we go beyond three variables, we often just start denoting those different variables with subscripts, like x sub 1 through x sub 4 being our 4 variables. So that was all in the last video. Then we also introduced this notation. K is a field, and then you've got these square brackets, and then the variables x sub 1 through x sub n. This represents the set of all polynomials in these n variables with coefficients in the field K. So this is just a single polynomial, and we can choose any one of these fields. Let's say f is an element of this set right here. So that is the set of polynomials with coefficients that are real numbers in variables x, y, and z. That's just a concrete example. That set there is a concrete example of one of these. This is a set of polynomials in variables x sub 1 through x sub n with coefficients in k. Now, this set does not satisfy the properties of a field. You can add them, you can subtract them. The multiplication and addition are both commutative and associative. We've got a multiplicative identity and an additive identity. But the only problem here with this is that we don't have a multiplicative inverse. And so that means that division doesn't really hold. Now, if you're saying to yourself, well, what do you mean division doesn't hold? I can divide a polynomial by a polynomial. You can, but when you divide a polynomial by a polynomial, you don't get a result that is also a polynomial. So because of that, we call this a commutative ring. And it's such a common commutative ring that we call it a polynomial ring. A commutative ring is just like a field, except it doesn't have multiplicative inverses, because you can't take any polynomial and find another polynomial that you would multiply it by to get 1 every time. Like, it just doesn't work that way. And then the very last thing that we talked about, which is a very important concept for algebraic geometry, is this concept of an affine space. And again, we're just using new terms, new terminology and slightly new notation for things that you're already familiar with. You've dealt with affine space before, you just didn't call it affine space. If you have some field K, which might be the set of real numbers or the set of complex numbers or the set of rational numbers, for example, we're going to denote n-dimensional affine space by k to the n. And that is a set of n tuples where all of those n numbers, a sub 1, a sub 2, a sub 3, all the way through a sub n, are elements of K, or in other words, they belong to that field K. So if you have taken calculus 3 and you're familiar with R3, that is the set of all x, y, z such that x is a real number and y is a real number and z is a real number. That's an example of three-dimensional affine space for the particular field given by that R, the field of real numbers. Okay, so this video is about taking what we talked about here with polynomials and affine space and linking them. Polynomials are going to allow us to link algebra and geometry, and that linking between algebra and geometry is related to this linking between a polynomial and affine space. We're going to talk about two meanings of f equals 0, or if somebody says, is f equal to 0? We could interpret that in two ways. We're going to talk about what those mean. We're going to talk about this case when these two meanings of f equals 0 are equivalent to each other. We'll define equality. We're going to say that two polynomials are equal under certain conditions. We'll state the fundamental theorem of algebra, and then we'll talk about the definition of algebraically closed. That's a new term. That's the plan. Hopefully this video doesn't get too long. Let's start with the first one. Well, how do polynomials allow us to link algebra and geometry? Now, this is another one of those things where I would say you already know the answer to this. We know how polynomials allow us to link algebra and geometry, and because we know about functions. So if you have a polynomial f, which can be denoted this way, remembering that x to the alpha is a product, x sub 1 to the alpha 1 times x sub 2 to the alpha 2, all the way through x sub n to the alpha n. And this is a polynomial in variables x sub 1 through x sub n with coefficients in the field k. This defines a function. Now, since x sub 1, or since a sub alpha is a member of k in the first place, it's an element of that field. If you replace x sub 1 through x sub n by alpha sub 1 through alpha sub n, so we're given this point in n-dimensional affine space, we can take each of those values from n-dimensional affine space, and we can plug them in for x sub 1 through x sub n. When you do that, you've got these numbers in the field k. You're raising them to powers. Those are still going to be in the field k. Then you're multiplying them by numbers in the field k. So that product will be in the field k. And then you're adding all of those together. And because of the properties of a field, that will also be in the field k. When we do that, the result of this is a number, and that number is in the field k. So I'm just going to say, since this is in n-dimensional affine space and the a sub alphas are in k, f of a sub 1 through a sub n is also in k. But it's in k for all of the reasons that we just talked about. When I plug these in for all of the x values here, remember that that's a product, and I raise those to powers and I multiply by a sub alpha, and then I add all of those together, because of the properties of a field, which we talked about in the last video, the result is a member of the field as well. So in this way, f is able to take values from k sub n and map them to values in k. And since we're able to do this, that's going to allow us to link algebra and geometry. Okay. And I think that that makes sense, because once you have this mapping, once you have a way to get from this expression, which defines a polynomial, to a set of n plus 1 tuples in n plus 1 dimensional affine space, now we're able to link a particular polynomial to a particular picture. That's allowing us to link algebra and geometry. So just like this very simple example, we have f of x equals x squared. Well, f takes a real number and it maps it to a real number. And then the graph is the set of ordered pairs x and y, where y is given by f of x. And we know that that graph lives in two-dimensional space, and it looks like this. Because of this mapping, we're able to draw this. We're able to come up with this picture of what this function, this polynomial, actually looks like. So that's what I mean when I say that this polynomial allows us to link algebra and geometry. and you've done it before. We're just doing it in n-dimensional space, and it looks a little bit more abstract. But if you've done this, you've really done this, we're just using new notation and new terminology so that we can expand what we know so well, into a more abstract setting and work with functions of more variables and polynomials, sets of polynomials, or polynomial rings that are defined by different fields over here. Okay. So with that in mind, that actually raises some questions. Now, if someone asks you, yeah, is f equal to 0? There are actually two meanings to that. Now, if you're saying there's only one meaning, you're right when you're talking about the set of real numbers and other sets that are similar to that. But here are the two meanings in general. So if somebody is asking you if f equals 0, they're asking you, or they may be asking you, yeah, is f the 0 polynomial? Or in other words, are all of the coefficients and the a sub alpha in our notation equal to 0? If they are, then this is the 0 polynomial. Basically, you've got that, which is of course 0, no matter what a sub 1 through a sub n happen to be. So that's one meaning of f equals 0, or is f equal to 0. The other thing they could be asking you, if they're saying, does f equal 0, is they might be saying, is f the 0 function? And there are other meanings for f equals 0 as well. We'll say, is f equal to 0 for a particular value of a sub 1 through a sub n? That's a third question, but we're just going to focus on these for right now. If somebody says, is f the 0 function, what they mean is f of a sub 1 through a sub n equal to 0 for all points a sub 1 through a sub n in n-dimensional affine space for that particular field k? If so, then f is the 0 function. So you might think that there's not a distinction between these. Isn't f equals 0 and f equals 0 for all values of x the exact same function? And it is in those number systems that we're familiar with. When we're talking about the real numbers, when we're talking about the complex numbers, in both of those cases, being the 0 function and being the 0 polynomial follow from each other. This implies this and this implies this. It goes both ways. But these are not necessarily equivalent in general. And that's a little bit surprising, and that contradicts our intuition because we're so accustomed to the real numbers and the complex numbers. Now in the book, it talks about a particular example. It's defining a set F2, and it consists of two values, 0 and 1, and it defines 0 and 1 in this way. It turns out that 0 plus 0 and 1 plus 1 are going to be defined to be 0. And 1 plus 0 and 0 plus 1 are both defined to be 1. And 1 times 0 and 0 times 1 and 0 times 0 are all defined to be 0, and 1 times 1 is equal to 1. So it's kind of like modular arithmetic. It's like every time I add a bunch of ones together, if the result is even, I'm going to call that 0, because 1 plus 1 is 0. If the result is odd, we're going to call that number 1, because 3 is 1 plus 1 plus 1, and 1 plus 1 is 0, and 0 plus 1 is 1. So all of our even numbers map to the 0, and all of our odd numbers map to the 1. it turns out that this is a field. If you're not sure, you can check it out. If you wanted to check it out, you would have to check the commutative property, the associative property for both addition and multiplication. You would want to check the distributive property. You'd want to check and be sure that you have an additive identity and multiplicative identity. And actually, I think we could check that right now. When you're saying that we have an additive identity, what that is saying is that you can take any number in this set and add a particular number to it and get that number back. And it turns out the additive identity in this set is 0, because if you take any number in that set and you add 0 to it, you're going to get that number back for every A in that set F2, which is for every A in the set 0, 1. And the multiplicative identity is 1, because you can take any number in the set, multiply it by 1, and you get that number back. So 0 times 1 is 0. 1 times 1 is 1. So that is the multiplicative identity. So you want the additive and multiplicative identities, and then you should probably check additive inverse and the multiplicative inverse. So that's saying that for every number in this set, there's another number that you can add to it so that you get 0. Well, 0 plus 0 is 0, and 1 plus 1 is 0. So both 0 and 1 have additive inverses, so that checks out. As far as multiplicative inverses are concerned, that is a number that you can multiply by that number and get the number 1 back, except for 0. When you're talking about multiplicative inverses, this is what it says in the axioms for a field. They say for all A in the field that you're looking for, where A is not equal to the additive identity, which we typically denote by the 0 element, there exists a number C in that particular set such that A times C is equal to 1. Since we're restricting A to not be 0, and this set only has 2 numbers, 0 and 1 in it, well, then we can assume that A is equal to 1, and of course 1 times 1 is 1. So this is the multiplicative inverse. That's how we prove that. So this is a field. If you want, you can check out all of the others as well. But this is an example where being the 0 polynomial and the 0 function would not be the same thing. So let's say we are in this field and we've just got f as a function of a single variable x, where the field k is actually this field that's denoted by this f2. Well, if f is this one, so let's say we've got x plus x squared. And if you want, you could, you could write that this way. This is the 0 function, but it's not the 0 polynomial. Now, it's obviously not the 0 polynomial, because in order to be the 0 polynomial, this would have to be like 0 times x plus 0 times x squared plus 0 times x cubed, infinitely many 0 terms. and you wouldn't see anything over here. So this is not the zero polynomial because the coefficients are 1 and 1. And we've got powers of x over here, x to the first and x squared. So just by definition of a polynomial and the zero polynomial, this is not the zero polynomial, but it is the zero function. And if you're not sure, remember what that means. We're saying that something is a zero function if you can plug in any value from the field, that n-dimensional affine space actually that you're interested in, and you get 0 back for every single member of that n-dimensional affine space. Now this is just one-dimensional affine space because you have a single variable x here. So the claim is that a plus a squared is equal to 0 for all a in the set F2, or in other words, for all a in the set with elements 0 and 1. And if you're not sure, because it's such a short list, you can check it out. Just plug in 0. Of course, 0 plus 0 squared is 0 plus 0, which is 0. And then substitute in 1. That's the other possibility. We've got 1 plus 1 squared. It's 1 plus 1, and 1 plus 1 is defined to be 0. So for every value in this field, F2, we get 0. So this is a zero function, but it's not the zero polynomial. So these are not necessarily equivalent. Now, of course, there's a third definition of is f equal to 0. We might be saying is f equal to 0 for a particular value of x. So we might be saying is f equal to 0? Well, it is equal to 0 at these values, but we're not concerned with that here. These two are something that we tend to think of as interchangeable, but we tend to think of them as interchangeable because being the zero polynomial and being the zero function are exactly the same in the real number system. So that leads us to our next proposition. This is proposition 5 in the book, excuse me. So remember, zero polynomial means all the coefficients are equal to 0, and zero function means the function value is 0 for all n tuples in n-dimensional affine space. Wow, that is really bright for some reason with that document camera today. Okay, so let's look at that first proposition. Or I guess it's not first proposition, it's proposition 5 in the book that we're outlining. And it says, let's let K be an infinite field. And all that means is that if you were to look at the set K, it has infinitely many values in it. So examples of infinite fields include the real numbers. That's a field that has infinitely many values in it. The complex numbers, also a field with infinitely many values. The rational numbers, that has infinitely many values. It's countably infinite, but it's still infinite. So those are all examples of infinite fields. If you're saying to yourself, what's an example of a field that's not infinite? How about F2? That's one that's not infinite. So for this proposition, let's say we're talking about an infinite field, a field that looks like this. And let's suppose that we're talking about a particular polynomial in this polynomial ring with coefficients in K, and we're talking about polynomials in n variables, x sub 1 through x sub n. Then, if that's true, then f is equal to 0 in that polynomial ring if and only if this is the zero function. Now, if you are new to logic, this if with the two F's is not a spelling error. that just means that the implication goes both ways. So this is saying if K is an infinite field, oops, that is a spelling error, then F equals 0 is an element of this set if and only, or F equals 0 in this set. I guess I don't want to write is an element of. F is equal to the 0 function in the polynomial ring if and only if, or sorry, F is equal to the 0 polynomial in the polynomial ring if and only if F is the 0 function. So that's what we mean over here. The 0 polynomial. So that means all of the coefficients a sub alpha are equal to 0. And over here we're saying F is the 0 function. So this proposition is claiming, and we have to prove it, it's claiming that if K is infinite, then if F is the 0 polynomial, then F is the 0 function. And if F is the 0 function, then F is the 0 polynomial. It's saying P implies Q and Q implies P. It goes both ways. This statement implies this statement and this statement implies that statement. That's what if and only if means. Sometimes you'll see it written that way. It's just an equivalence. Like this is equivalent to this as long as we're talking about an infinite field K, like one of these, not like that. Okay, let's prove that this is true. One direction is really obvious, but I'm going to state it for you just in case you're new to proving things. So let's first prove that if F is the 0 polynomial, then F is the 0 function. So let's say that F is the 0 polynomial. We assume that this is true, and then we try to show that this is true. So we'll say that this is equal to this. So all the a sub alpha are equal to 0 for all alpha, and we've got a finite number of alpha there. I know it's a little weird when they're all 0. Then obviously, it does not matter what I substitute in for a sub 1 through a sub n. This is going to be sum over alpha of 0 times a sub 1 to the alpha 1 times a sub 2 to the alpha 2 times a sub 3 to the alpha sub 3, all the way through a sub n to the alpha sub n. This is just the expanded form of x sub 1 to the alpha 1, x sub 2 to the alpha 2. That's this expression, which is the expanded form of this expression. Because remember this, or this here, excuse me, is just shorthand for this. It doesn't matter what I plug in. If I multiply them all by 0 and I add them together, I'm still going to get 0. And since it does not matter what I substitute in over here, this is true for all alpha or a sub 1 through a sub n in n-dimensional affine space. So that means that if f is a 0 polynomial, then sort of obviously f is the 0 function. So we have proved that if this is p and that's q, we have proved that p implies q. That's the notation that we tend to use when we're learning how to prove things, when we're just getting started with proof. Now the second case is to go the other way. This one's going to take a little bit more time. It says, if f is the 0 function, then f is the 0 polynomial. And of course, in both cases, we are assuming that K is an infinite field. So it satisfies all of the field axioms, and it has infinitely many elements. Now this is easiest to prove by induction. So we're trying to prove that Q implies P so that we can show that P implies Q and Q implies P, therefore they're equivalent to each other. Now it's really helpful if you've had a class in just fundamentals of theorem proving to go through and learn about direct proofs and proof by contradiction and the principle of mathematical induction and all of that. It's really helpful so that you're not just sort of taking my word for it. But what we did here is pretty much what we want to do here. What we do is if we're trying to prove that P implies Q, we assume that P is true. So we assume that F is the zero polynomial in this case. So this is our P. If this is true, we're saying then this is true. So this first one is P, the second one is Q. So we assume that P is true, and then we try to imply that if P is true, then this has to be true, that this automatically follows from the fact that this is true. That's what this statement says. And that's what we want to do over here. This time we've just reversed the roles. If this is P and that's Q, and here we showed that P implies Q, now we want to show that Q implies P, that it goes the other way as well. So we want to show that if F is the zero function, then F is the zero polynomial provided that K is an infinite field. And now we're going to do something called proof by induction. And basically the way proof by induction works is you start by showing that something is true for n equals 1. So we want to show that this is true when we are not dealing with x sub 1 through x sub n, but we're just dealing with x, functions of a single variable. So we're going to start with that. And I'm actually going to cheat a little bit here because I'm not going to prove that it's true in n equals n. I'm just going to appeal to what you know, appeal to your intuition. So let's say that we're going to assume that K is infinite. It's an infinite field. And F is a polynomial with coefficients in K, and it's a polynomial of a single variable. Or actually, it's a polynomial of a single variable with coefficients in K, yes, but we also want to assume, that this is true. And we're going to assume that F is the zero function. So that means that F of A is equal to 0 for all A in this infinite field. Well, we know that if F of A is equal to 0 for all A in this infinite field, and A, this is not an n-tuple, this is just a single variable, then we know that this has to be the zero polynomial. It's going to have to be 0 all the time. And that's because of what we already know about the number of roots of a polynomial of a certain degree in a single variable. So I'm going to recall and apply this fact that I know. And if you're saying, how do you know that you get to assume that that's true? How do you know that we don't have to prove that too? We really don't. I guess it depends on the context, whether you get to assume that that's true. But let's say we already know that every non-zero polynomial let's say of degree m in this set of polynomials in a single variable with coefficients in the field k has, let's say, a maximum of m roots. And you know that this is true, just from what you know about complex numbers and real numbers. We actually haven't proven this in general, so we're just assuming that what we know about complex numbers and real numbers is true in general. So maybe we're cheating a little bit with this proof by saying that we know that this is true. But we're really relying on what we know about real numbers. We know that if we're dealing with an nth degree polynomial, like in a college algebra class, let's say it's a third degree polynomial, you know that you can have at most 3 roots. Third degree polynomials, you know, have a tendency to look like that. So you can have 3 roots. Or maybe you only have 1 root. Maybe it's just y equals x cubed. It's just that x equals 0 root repeated 3 times. But that's generally the shape of a cubic polynomial. It has 3 roots here, it has 1 root there. Maybe you've got a cubic polynomial that behaves like this, where it just sort of touches and turns around and then it goes through. So you might have 2 roots, but you either get 3 roots or 1 root or 2 roots. You have a maximum of 3 roots. There is no way that a cubic polynomial could give you 4 roots. You already know that that's true. We're saying that that's true for every field k. We're just stating it. And knowing what you know about factoring polynomials, you can always write a polynomial as a constant times, if it's a polynomial in x, as x minus a root times x minus a different root times x minus a different root, and you'd have up to n factors there, or m factors if it's degree m. Those are things that you've already studied in pre-calculus. So we're assuming that's true for every infinite field. If you're dealing with a single variable, so when we're trying to show that this result is true, we're going to say, oh, we know that this is true, but actually we only know it's true for the reals and the complex numbers. So maybe we really haven't even proved that it's true for n equals 1. But if we get to assume this, then we've proved it. Because this says that if we know that k is an infinite field, and f is a polynomial in a single variable x with coefficients in that field, and f is the 0 function, so that it does not matter what a is in that infinite field, we always get 0. Well, that means that this function f has infinitely many roots. That's equivalent to that. And it's equivalent to that because we said earlier that k is an infinite field. So for infinitely many values of a, we get 0. So this has infinitely many roots. And we know this fact. I'm going to put that in quotes. We know this fact, that every non-zero polynomial of degree n has a maximum of m roots, given what we know about real numbers, given what we know about complex numbers. That in this part is the part where I'm like, we know it, we don't really know it, we haven't proved that yet, that's okay. We're going to assume that that's fine because the author of our textbook did when they did this proof by induction. But if we have infinitely many roots and every non-zero polynomial of degree m has a maximum of m roots, well then that means that this cannot be a non-zero polynomial. Sorry about the double negative there, but if f is not a non-zero polynomial, what does that mean? Well then f must be the 0 polynomial. So based on this assumption that we may or may not make, which may or may not have been a fair assumption, we know that this result that if f is the zero function, then f is the zero polynomial is true when we're dealing with an infinite field k, and provided that this fact is true, that every non-zero polynomial of degree m in this set here has a maximum of m roots. And again, it appeals to our intuition based on what we've studied and what we know about polynomials already. Okay, so that's the beginning of a proof by induction. With a proof by induction, this is basically what you're going to do. So we call this a proof by mathematical induction. Oops, induction. It's been a long time since I've done one of these. We used to call it PMI when I learned how to do this many, many years ago. Basically what you do is you show that it's true for n equals 1 often, or n equals a particular value, you know, maybe it's n equals 3. And then you show that if it's true for n equals 3, it must be true for n equals 4. And if it's true for n equals 4, it must be true for n equals 5. So you show that the statement or the result that you're trying to prove, that's this guy right here. Usually it's n equals 1, but we would be fine with starting with a different value of n. It would just not be true for all values of n. It would just be true starting with that one and then every one after that. So we show it's true for the first value, and then we want to show that if the result is true for n, it must be true for n plus 1, or it must be true when when n is equal to n plus 1. So if it's true for 1, and then we've shown that if it's true for n, it's true for n plus 1, then proving it was true for 1 implies that it's true for 2, and proving that it's true for 2 implies that it's true for 3, and proving it's true for 3 implies that it's true for 4. But by doing this, we're saying it's true for all of those, because it's true for this one, and then every other one after that, because if it's true for n, it's also true for n plus 1. And then we can say, if that's true, then the result holds for all n. For n equals 1, 2, 3, and so on, by the principle of mathematical induction. That's PMI. Okay, so we have shown, or maybe kind of cheated, when we have shown that this is true for n equals 1, because we have used the fact that every non-zero polynomial of degree m has a maximum of m roots, which we know to be true for the reals, which we know to be true for complex numbers. And we're assuming that we are dealing with an arbitrary infinite field in a single variable here. So provided that that holds, and that we're not sort of cheating by just ignoring that fact, we know this is true for n equals 1. Now we want to show that if it's true for n, then it has to be true for n plus 1 as well. If we can show that, then we can show that this result is true in general. And if we can show that this result is true, we're saying that Q implies P, and earlier we showed that P implies Q, and that means these two results are equivalent to each other. So that means if f is the zero polynomial, it's the zero function, and if f is a zero function, it's a zero polynomial. Of course, again, assuming that K is an infinite field, which is what this particular proposition is about. Okay, so let's try to do this next part. It says, show that if the result is true for n, it must be true for n plus 1. That's the next part of our mathematical induction argument. Okay, so let's assume the result is true for f in this polynomial ring. So f is a function of n variables, x of 1 through x of n. Or in other words, if f is the zero function, in this space. So every a sub 1 through a sub n that you plug into this gives you a 0. Then f is the 0 polynomial. In the same set, that same polynomial ring. So we're assuming that this implies this when we're dealing with n variables. Now the question is, well, if that's true, what can we say about 0 functions in the set of polynomials with coefficients in the infinite field k that have n plus 1 variables? So let's let f be a polynomial in this field now. And I guess I'm using a different function over here. I'm using f here twice, but this f is not the same as that f. Maybe I should use a different letter. Let's use h. So let's let h be a polynomial in the polynomial ring with n plus 1 variables instead of n variables. And we're trying to prove that this is true. So let's let h be the 0 function in this space. So what that assumption means is, again, that h of a sub 1 through a sub n plus 1 is equal to 0 for all a sub 1 through a sub n plus 1 in this n plus 1 affine space, n plus 1 dimensional affine space. That is the definition of being the 0 function. Now, if we want to, we can take all of the powers of x in here. So h is going to be something that looks like this. Oops, a sub alpha times x to the alpha. So that's x sub 1 to the alpha 1 times x sub 2 to the alpha 2, all the way through x sub n to the alpha n times x sub n plus 1 to the alpha sub n plus 1. Now, if we want to, we can collect powers of x sub n plus 1. So we can think of this in a different way. We can think of this as g sub I times, or evaluated at, x sub 1 through x sub n times x sub n raised to the I. And this is for I equals 1, or I equals 0, excuse me. Should be n plus 1 there, through n plus 1. Now, if you're saying to yourself, how is that possible? Again, just imagine taking this and rearranging it. You've got all of these powers of x over here, and then you've got one variable that you're particularly interested in, the n plus 1th variable. So we're just going to say, let's look at, let's group this differently, so that we've got all of the powers of that n plus 1th variable over here. Just as an aside, so let's say that h is equal to 2 x y squared z minus 3x cubed y squared z plus 2x squared z to the 4th. Well, if the variable that I'm interested in is that x sub n plus 1, if the x sub n plus 1 is the z here, but all this is saying is that I can take some of these and I can factor out a z to some power. So I've got this guy times z to the 1st, and maybe let's put in another one over here. Then I've got this guy, 2x squared minus x times z to the 4th. So this would be g sub 1 of x and y. and this would be g sub 4 of x and y, because this is the polynomial that multiplies z to the first, and this is the polynomial that multiplies z to the fourth. That's what we're doing here. This subscript here goes with that exponent there. But do you see how it's possible to do that for any variable? We could group these with the y's together. So we could take the y squared out of this, and we could say that there's no y's over here. And so we could write this as a polynomial of x and z times y squared. And we could write this as just a polynomial times y to the 0. And that's the I equals 0 term from here. So this rearrangement is really just doing this. I know it looks bad, especially if you're not used to doing proofs and you're not used to all this symbolism. But this is really just the same as that, just rearranged. It's just a regrouping. So I wanted to give you a concrete example so that this makes a little bit more sense to you. Okay, so let's say that h is equal to this. H is equal to this, which is equal to this, and now we're regrouping it in this way so that we've factored out all of the powers of the variable we're interested in. So we'd have, if we're interested in z here, z to the 0, z to the first, z to the second, z to the third, z to the fourth, and then we'll stop. Okay. And I'm not even 100% sure that that should be an n plus 1 there. Because I doesn't necessarily have to go from 0 to n plus 1. I mean, this could be, z to the 100th, and that would be totally fine, even though we've got 3 variables. Let's just use a capital N over there. Okay, so we've done that. So we can take this h and we can write it this way. Now this g sub 1, or g sub I, which is a function of variables x sub 1 through x sub n, this is a polynomial in not this n plus 1th dimensional polynomial ring. It's a polynomial in this nth dimensional polynomial ring. So yeah, that's good and that's important because remember what we did over here. We assumed that if f is the 0 polynomial in this nth dimensional polynomial ring, or this polynomial ring involving n variables, x sub 1 through x sub n, I guess I'm saying it wrong. If that's true, then this is true here. But we have not yet proven that this implies this when we're dealing with a ring in n plus 1 variables instead of n variables. But look, we've rearranged it. So we've got polynomials in n variables here, and then we're tacking on this n plus 1th variable. Okay, so we've collected the powers of x sub n plus 1, and we've written this in this way. And now we're going to have these g's in the polynomial ring with n variables. Now, if we can show that each of these g's must be the 0 polynomial, or each of these is the 0 polynomial. Well, if I take each of those zeros and I multiply them by x to some power, well then h has to be the 0 polynomial in a space where we have a single variable. And remember, because of this little assumption that we made, if we're dealing with an infinite field and we're dealing with a single variable, the fact that f is the 0 function implies that f is the 0 polynomial. So basically, the idea is this. If we can prove that all of these g's are 0, well, if all of these are the 0 polynomial, if these are all 0 polynomials, then h is just the sum of a finite number of zeros times these guys. So that is going to be a function of a single variable. And then because of our earlier result, we can say that h is the 0 polynomial as well, because we've already assumed that h is the 0 function. So we're trying to show that h also has to be the 0 polynomial, provided that k is an infinite field. Okay, so the next goal is to show, in order to get to that step, we need to show that these guys are all equal to 0. So let's choose a particular value or a particular n-tuple in n-dimensional affine space. Then if we evaluate h at that n-tuple, and we still have that x sub n plus 1 as a variable in there, what we get is this. Now this, we know, is equal to 0. Well, first of all, we should say that this is an element of this space. It's part of the polynomial ring with coefficients in k in the single variable x sub n plus 1. Now, since h is also the 0 function, that was our initial assumption, then, h of a sub 1 through a sub n is equal to 0. Well, for every a sub 1 through a sub n plus 1 and k to the n plus 1, including all of these. But now we've got particular numbers in here. So we've got h is the 0 function, so this is true, and we have substituted in these particular values. Now we have this function of a single variable, which is a function in this polynomial ring here. That's equal to 0 for every x sub n plus 1 in k. And remember, k is an infinite field. So this is for infinitely many values of x, we're getting 0. And then since this is now a function of a single variable, and this is equal to 0 for infinitely many values of f or x, that means we've got infinitely many roots for this. And then by this fact that we assumed at the beginning, so every non-zero polynomial of a certain degree should have a maximum of m roots. Since we've got infinitely many roots, we know that this cannot be a non-zero polynomial. So h is the 0 polynomial. In this polynomial ring, k of x sub n plus 1. Now, if h is that 0 polynomial there, well, that means that all of these g's from back here must be 0. Because we're taking each of those zeros and we're multiplying them by x to some power for all the possible powers of x sub n plus 1. So now we've shown that all of these guys must be 0. And since all of these guys are 0, and this was for some arbitrary a sub 1 through a sub n in n-dimensional affine space, since that was arbitrary, that particular choice that we made in order to do this, this is going to be equal to 0 for all of these guys. See that switch as we go from here to here? That's a big deal. And that means that all of these are the 0 function. I'm writing, should I say NKN? Is that the right way to say it? So these guys are the zero function, and that means the GI are the zero polynomial. Or each of those are the zero polynomial because of our assumption that we started with way back here. We assumed that if f is the zero function in this polynomial ring, then it's the zero polynomial in that polynomial ring as well. So if this is the zero function, then that means that's the zero polynomial. Since these are all the zero polynomial, well, then I have a bunch of zeros multiplying x to some power for every x sub 1 through x sub n. Watch that, be careful about that. When we say that g sub I is the zero polynomial for I equals 1 through capital N, what we're saying is that the coefficients, that's equivalent to saying that the coefficients a sub alpha sub I, for each of the g sub I are all equal to 0. So it does not matter what x is. So this is equals 0 because of our earlier assumption that the result that we were trying to prove, that being the zero function implies you're the zero polynomial, is true when we have n variables. And that means that if these are literally a bunch of zeros, no matter what x is, if I'm taking a bunch of zeros and I'm multiplying by x sub n plus 1 raised to the I, well then h must be the zero function. Or not the zero function, I'm sorry, the zero polynomial. Because I've got 0 times x to some power plus 0 times x to a different power. And if you're saying, well, that's only true at a sub n through a sub, or a sub 1 through a sub n, remember that switch happened from being interested in this particular value to every value. And when we talked about every value, that's equivalent to saying that g is the zero function. And then this is the jump from here to here when we said that we're going from the zero function, which always gives you 0 when you plug in all the values in n-dimensional affine space, to going to the zero polynomial, which means that every coefficient of the polynomial is equal to 0. Because that's what that equivalence is right there. This is the same as this. And if all of these are 0, no matter what x sub 1 through x sub n are, we end up with a bunch of zeros times these guys. So h has to be the zero polynomial as well. Okay, so that was a lot of work, but we have just shown that if h is the zero function, then h must be the zero polynomial. We've just shown that if that result, this result right here, was true for n, it must be true for n plus 1. Then since it was true for n equals 1, and it's true, being true for n means that it's true for n plus 1, that means it's true for n equals 2, and 3, and 4, for all the natural numbers. So this result is going to hold no matter how many variables you have. So we have just shown that Q implies P by the principle of mathematical induction. So we'll say since the result, whoops, is true for n equals 1, and being true for n variables implies that the result is true for n plus 1 variables, then the result is true for all natural numbers n. So n equals 1, 2, 3, 4, all the way to infinity, countable infinity, so on. You could have a million variables. and it would still be true because a million is finite and it's a natural number. Okay. So we have just shown that this is true by the principle of mathematical induction. So if f is the zero function, then f is the zero polynomial when k is an infinite field. And if f is the zero polynomial, then f is the zero function. So these two are equivalent to each other when k is an infinite field. Now, if you're saying, when did we use the fact that k was an infinite field? I think we used that fact right here. When we started here, when we said that we know that every non-zero polynomial of degree m in a single variable has a maximum of m roots. We used the fact that k was an infinite field right here. And let me see on the second page, did we use the fact that k was infinite anywhere else? No, I don't think we did. So I think it kind of is cheating using this fact right here, because we know it's true for the reals, we know it's true for the complex numbers, but I don't think we ever proved that it was true for this. That might be a fun little exercise to prove as well. Okay, so now we know that if k is infinite, being the zero function and being the zero polynomial are interchangeable. If you're looking at the zero polynomial, you're talking about the zero function, and vice versa. There are a couple of other facts. Here's a corollary. It says let k be an infinite field. And let f and g be elements in this polynomial ring with n variables. Then f is going to equal g in the polynomial ring. If and only if f and g are the same function. Now again, whenever you say is f equal to 0, now we say f is equal to g in this polynomial ring. You have to ask yourself, well, what does this mean? Again, we're saying that two functions are equal in this ring if, or this means, this is equivalent to saying that f and g have the same coefficients. So those a sub alpha and the formulas for the two polynomials f and g have the same coefficients in k. And this is pretty easy to prove. You would just look at the function f minus g, show that it's equal to 0 all the time. Therefore, it's a zero polynomial, and then you can just take an equation and rearrange it. It's a very, very easy proof. So I think I'm going to leave that to you. If you want to prove that, you can. But this is just saying that if two polynomials have the same coefficients, or if they have the same coefficients, then the functions are the same function. Every n tuple that you plug into this function and every n tuple that you plug into this function will give you exactly the same value. F of a in this set and g of a in that set are going to be equal to each other. And this is just a natural implication of what we just said with that last proposition. Another theorem that's really important in algebraic geometry is theorem 7 in this chapter, or in this section. It says that every non-constant polynomial f in the complex numbers, or not in the complex numbers, excuse me, in the polynomial ring in a single variable where the field is the field of complex numbers. Every non-constant polynomial has a root in C. This is also known as the fundamental theorem of algebra. Now, this is equivalent to saying that C is algebraically closed, another important definition for algebraic geometry. Let's say that we say a field K is algebraically closed if every non-constant polynomial in the set of polynomials in a single variable with coefficients in K has a root in K. So when it's saying that every non-constant polynomial in this set has a root in C, and then this is the definition of algebraically closed, it's saying the exact same thing to say that the set of complex numbers is algebraically closed. So it's a field, it's an algebraically closed field. So that means any polynomial in a single variable has a root in the complex numbers. So just as an example, x squared plus 1, that's a polynomial. We can think of that as a polynomial with coefficients in the set of complex numbers. The coefficients are 1 and 1, and the coefficient of x to the first is 0. And then there are infinitely many coefficients that are all equal to 0 for all the higher powers of x if you want to look at it that way. But this has a root in C. When we say that C is an algebraically closed field, we're saying that this can be solved in the real numbers or in the complex number system. So if we subtract 1 from both sides, you do your pre-calculus thing, and you get x is equal to plus or minus I. We actually have 2 roots to this polynomial in this polynomial, or in this field C. Now, we know that this equation does not have a solution in the real number system. So the set of real numbers is not algebraically closed. Because there are plenty of non-constant polynomials in this polynomial ring in a single variable where coefficients are in the reals that do not have roots in the reals. And x squared plus 1 is one of them. X squared plus 1 is never equal to 0 in the real number system. One way that you can see that is you can just look at y equals x squared plus 1. That's never equal to 0. The y values on that graph never cross the x-axis. So we're never going to get a y value of 0 out of this if we stay in the real number system. But if we go over to complex land, now we actually get two different answers. Now that's just a particular example that sort of illustrates that the reals are not algebraically closed and the complex numbers are algebraically closed. It's a very familiar example, but hopefully that helps you understand what these 2 statements mean, what that definition means. This says that every non-constant polynomial in this polynomial ring has a root in K. So if you're saying that something is algebraically closed, you get to assume that for any polynomial, even if you can't think of the roots, even if you can't solve the equation, you could just write down a polynomial. You're going to have a root in the complex number system. You're going to have a complex root, provided that the coefficients are complex numbers. Now, over here, we're saying that even if all the coefficients are real numbers, there's no guarantee that there's a real number out there that was going to give you a 0 over here. So the reals are not algebraically closed. And that'll be very important later. So that is the end of this discussion. Next time, come back and we'll learn more about polynomials and their graphs. And we're going to tie this idea of affine space and polynomials to something called an affine variety.